Okay, in this video I want to talk a little bit about the physical meaning of the wave equation. Okay, so I'm going to define it this way. Let U be the displacement of a plucked string, so like a guitar string, at position x along its length and at time t. So it depends on where on the string and it depends on what time. So that's my picture. It's a great picture. Pluck. So we have a string going from 0 to L. We pull on the string or push on the string or whatever, and then we let it go and it should wobble back and forth. And so how far this particular spot on the string is pushed away from the center is going to depend on the time. It's also going to depend on which position did I pick. So the motion of the string is going to be modeled by where on the string and how many seconds have passed. Okay, so the equation that we're going to use is going to look really similar to the one we saw for the heat equation, only instead of second derivative of u with respect to x being the first derivative of u with respect to t, it's second derivative equals second derivative. And again, there's a constant, and for convention's sake, we're using a square as our coefficient, or our proportionality constant. Okay, so a is a constant, and this is the wave equation. I should also point out, you'll also see this same equation with different physical meaning showing up in things like electrical engineering courses. I'm not going to talk about every way that the wave equation pops up. I'm mainly going to be focused on how would we solve it. Okay, so real quick, just want to describe what some boundary conditions might look like. These are the ones I'm going to be solving an equation on in the following videos. If I say that u of x comma 0 is f of x, that means when t is equal to 0, we get a particular starting function. So at time 0, this is what the function looks like. This is what the displacement looks like. So that's actually saying the initial value of u, or initial displacement, is that particular function f. On the other hand, if I say the derivative of u at time 0 is equal to this, derivative with respect to time, if u is displacement, derivative of displacement with respect to time sounds an awful lot like velocity, and time 0 means it's the initial velocity. So if we think about guitar strings, we're used to plucking and then just releasing the string, but I guess you could, if it was a easy enough string to grab, you could throw it upwards or throw it downwards, and you'd have some initial velocity when you actually let go of the string. These other two are going to be typical equations. When x is equal to 0 or x is equal to L, our displacement is 0, and that means that the two ends are fixed. And there are other constraints we could set up, but typically these are the most common. Okay,